Okay. Hello, everybody. Good morning. First of all, it's a great pleasure for me to be here for the very first time in Malmo. I know that the weather is not that lovely, but so far everybody has been very lovely with me, so thank you very much. My name is Edson Yanaga. Currently, I'm a director of developer experience at Red Hat. My Twitter handle is @Yanaga, and many people get surprised about that, but I'm a Brazilian. So not the typical Brazilian you would expect, but yes, I'm a Brazilian Japanese. And I expect to have other Brazilians around here, but not other Brazilian Japanese. So I might be the only one here, okay? And today I'm going to talk about migrating to microservice databases from relational monolith to distributed data. In particular because I've been talking about DevOps and microservice for the past like 5-6 years. But the number one question that I always received when discussing microservices with different teams were, okay, but if the best practice to create a microservice architecture is to start with a monolith and then break into smaller parts, but I still have a legacy monolithic relational database, how do I deal with the data? I didn't have an answer for that, but in the past 2 years, I did some extensive research. I talked to many different developers and teams worldwide, tried to figure out how they were solving this problem, and I was able to collect some of the solutions that these teams are using successfully to distribute and later integrate their data into a microservices architecture. I also happen to be a Java champion and a Microsoft MVP, and I work for Red Hat. How cool is that, right? So, but it just means that the world has changed a lot. In the end, I think that open source has won. And just to give you another tip, with the result of all of this research, I've just published a book from O'Reilly, which has the same subject title as the subject of this talk. And today at the O'Reilly booth, 2 p.m., they brought some copies. I'll be signing and giving away some copies for free. So just in case you want to sign a copy, they brought, I think, 25 or something copies there for free. So just drop by. If you get a chance to get a copy, I'll be more than happy to sign that for you. But if you want the ebook version, Red Hat developers bought the royalties of the electronic version. So if you go to this URL, you'll be able to download the electronic version for free. I know it's a lot to type, but just in case you go to my Twitter profile @Yanaga, I have a pinned tweet with a link to the ebook so you can reach it from there, okay? And I'll apologize in advance. Usually I speak very slowly, but since today I have a lot of content to cover in only 40 minutes, I'll be speaking very fast. So forgive me for that, but or else I won't be able to cover everything. Now, I always like to start my talks with this quote from Forbes. Now, every company is a software company. You don't work for a bank, you work for a software company. You don't work for an industry, you work for a software company because software is changing the world. Sorry. Because basically when we're discussing that, many people call this digital economy, and I think digital economy or economics is an appropriate term for that, because I used to be one of those people that thought that economics had everything to do about money, but later I realized that economics has nothing to do about money, but has everything to do about people, because basically they study how people interact with each other in a system, and how they transition a system from one state to the other. So some motivations that people have to make these transitions can be love, can be hate, can be power, and can also be money. And when we're discussing digital economy, basically we're discussing how software is changing the way that people interact with each other. It's also important for us to remember that software is made by people, for people. Every time we forget these two social components in both ends, we can't deliver an optimal result into production. And some great examples of this new digital economy are that the largest car transportation company in the world owns no stock, which is owns no cars, which is Uber. The largest lodging company in the world owns no real estate, which is Airbnb. The largest online retailer in the world owns no stock, which is Alibaba. And the largest content network in the world produces no content, which is Facebook. All of these companies, they have something in common, is that they're changing the way that people interact with each other through software. So we as software developers, we have a very important role in this world because we are basically changing the behavior of people with the code that we're writing every day. So I believe that we better do it well. and better do it right, because we have a huge influence in everything that we have around us for the people that we love, that we don't even know. So we can make a positive influence. We can also make a negative one. So I believe that we can all make a choice. I believe if we're all here trying to learn and uncover better ways to deliver better software and faster into production, we already made a choice, and I hope that you can propagate this idea to as many developers as possible. And if I had to pick just one topic to talk about DevOps and microservice, because I know it's a large subject, I would say that the most important thing in the DevOps and microservices world is what I call the feedback loop, which is an essential human thing that we need in all of the human activities, because the feedback loop is the way that we can learn if we're doing the right thing right. And the feedback loop, our feedback loop is very limited, because I say that we as humans, we have a very limited capability of holding what I call context. So we are very good in trying to establish correlations when we can hold a certain amount of information in our brains for a certain amount of time. If we have too much information in our brains, we can't clearly establish this correlation between I'm doing this and I'm getting this result. And if I take too long to access if I'm doing this and get this result, also I can't establish this correlation. So I like to say I like to establish a very simplistic correlation, an oversimplistic correlation between the feedback loop and the software development world. Before joining Red Hat, I used to be an independent consultant, and I always talked to developers saying, well, we all know that we need to shorten our lead time, we need to deliver software faster into production and everything else, but what's the excuse that you have for not delivering software faster into production? And the number one excuse that I always received was that we can't deliver software faster into production because when we do that, we have too many bugs. So if we're releasing software every month, now we need 2 months to release our software because we need more time for testing. But people don't realize that the more time you have for testing, the more time you have for coding too. So when you release software every 2 months, you have twice the amount of bugs and not the half. So this is the human way of trying to solve the problem of bugs into production. We're trying to avoid releasing software into production because that's a painful thing. And unless I'm a masochist, I don't want to be suffering that thing like every month. I want to be suffering every 2 months or every 6 months or every year. I thought that 1 year was a long time enough for the delivering software into production. But this year, when I visited, I won't mention the name, but in one country here in Europe, I just talked to a team. They have a very large team of they had 25 distributed teams, and they were releasing software every 4 years. And you say, who can deliver software into production every 4 years? But after talking to the lead architect, I just realized why. That's because they produce software for the local governments, and you have elections every 4 years. So you just release software before the next government assumes, because you might not be hired to maintain that. So that's not your problem anymore. So if there are bugs, well, that's another team that will have to maintain that. So that's why they keep the pace of 4-year releases, but for most of us, it's simply unfeasible. So the correlation that I like to establish with you is that I like to say that what causes bugs into production when we release new versions of software is changes. So if you have changes, we have bugs into production. And changes technically in the DevOps world can be in 3 different areas. You can have changes in your data, you can have changes in your codes, and you can have changes in your environment. So this is the set of changes that usually causes bugs into production. But since I want to oversimplify this correlation, I would like to say that we as developers, what causes bugs into production into each new releases is changes in code. So the more changes in code I have between each one of my releases, the more bugs I have into production. Yeah. The human way is try to avoid releasing software into production, but the economical way of trying to solve this problem is to reduce the amount of changes that you have between each one of your releases. So if you have fewer changes, fewer bugs into production, if you can further even improve the amount of, reduce the amount of changes that you have between each one of your releases, so you can reach the ideal amount, one single commit of very few lines, and you just 30 minutes or 30 seconds or 1 hour later, you can release the software successfully into production. If you just deploy software into production and you have a bug, where is the cause of the bug? It must be on that 15 lines of code that you've just committed. So in this case, in this particular case, it's very easy for us to establish what we call correlation. I did this, I'm getting that into production because I'm solving a very small problem within my mind, which I call context. Just that I solved that with just 15 lines of code, and I'm releasing that 30 minutes later or 1 hour. It's a very short amount of time, so I still have that ideas in my mind, and I can establish this correlation. This is the easiest way for you to be able to solve the problem of bugs into production, but many people don't realize that. And technically, if I want to give you a technical term, this thing that I've just discussed in the DevOps world is called a batch size. Batch size is the amount of changes that you have between each one of your releases. The smaller the batch size, the better the quality of the software that you deploy into production. And if you want to dig into other technical terms, the smaller your batch size, the smaller is your lead time too, and the smaller your lead time, the smaller your cycle time too. If any of you here is like a process analyst or a Kanban expert, you know that these metrics, they are related. So if you reduce the batch size, you'll be able to improve everything else. But I always like to pick the batch size because when people tell you, you need to reduce your lead time, okay, I know I want to do that, but it's not easy. You need to reduce your cycle time. Okay, that's very hard for me to know if I'm improving that. But batch size is something that all of the developers can measure very easily. How many lines of code are you changing between each one of your releases? That's a very simple thing to measure. That's a very simple thing to improve. But even if you want to improve even further your batch size, there will be a specific moment in your improvement rate where we will be blocked from reducing your batch size because there's something called a maintenance window. And the maintenance window is that specific time of the day, the year, the month that you're allowed to release your new versions into production. Because every time you release your versions into production, you disrupt users. And you're not allowed to do that like in the middle of the day when everybody is buying or you're executing transactions or executing some procedures in your software. You need to do that when you have the least possibility of disrupting anything into production because you have bugs. But also, sometimes everybody has to log out and start it over again. Is not something desirable to be doing in the middle of the day. For you to be able to break the maintenance window and to be able to release software in smaller batch size compared to the maintenance window, you need something that we call zero downtime. You need zero downtime deployment, which is basically the ability for you to release new versions of software into production without disrupting the users. And for that, the simplest possible requirement is what I call blue-green deployments. I'll explain to you very quickly, just in case somebody is not aware of that. Traditional deployments, they have one deployment and client issuing requests directly to your deployment. If you want a blue-green deployment architecture, you need to add another component to your architecture, which is a proxy, which is basically something receiving requests on behalf of the deployment and forwarding to the backend. Now, if I want a blue-green deployment, I create two equal environments with the exact same capabilities, exactly same configurations, and each one of them is capable of handling 100% of my requests into production into any given moment. So if I want to perform a blue-green deployment, a zero downtime deployment, basically I just go to the green deployment, I ask the proxy to stop forwarding requests to my green deployment, I stop the servers, I copy the new artifacts, I start the servers. If I'm using a technology Java, I wait for the server to warm up by issuing some fake requests. And if everything went well, I can do the same process with the blue deployments, but people don't realize that blue-green deployments are not the only way for you to be achieving zero downtime, but it's also the safest way, because if anything bad happened with the green deployment, my new version is not working properly, I don't have to forward the request to the green deployment. Something went wrong, well, my production requests are going to the blue deployment, everything is working fine, and I have more time to assess what happened with the green deployment, so I can fix that with a new version. But if everything went well, I just repeat the same steps again with the blue deployment, and if it went well again, I can just ask the proxy to forward requests to both environments. In this case, the proxy can act as a load balancer, but the main purpose of a blue-green deployment is not load balancing, is simply failover. You need another a server which maintains the previous versions that you had into production, just in case your new version introduces new bugs or problems into your production software. But I'm discussing all of these, and you might be thinking, well, it seems kind of simple. It might be easy to achieve that. And I like to warn you that, well, with code is easy. I'm not saying the crafting code is easy, but I'm saying that no matter how hard is your code problem between your release versions, with data, is always much harder. That's why I say that code is easy, state is hard, because with code, well, worst case, and when the same state, you can have like two different kinds of state in your application. You can have ephemeral state, which is usually the state that you store like in your HTTP session, and you have persistent state. With ephemeral state, most developers choose to discard the ephemeral state. Well, the user will have to log back in again and lose everything that he or she was doing. If it was a small thing, okay, but if he or she was filling like a 200 field form and you ask he or she to start it over again, well, you have a very upset user there. But sometimes it's manageable. For persistent state, you're not allowed to dispose anything. The persistent state that is usually stored in a relational database, you need to keep that running. And the problem is that when you release a new version of software, usually your data schema is different between your versions. So how do I deal with that with relational databases or any other kind of persistent storage? So the question that I want to try to answer is that, what about my relational database? And the answer to be achieving that is that you need to automate everything. You're not allowed to apply the schema changes manually anymore. You need to use database migration automation tools. The two most popular ones in the Java world, and not only the Java world. I just realized that after some research, these two tools are very popular. The only world where it's not that popular is the Ruby world, just because Ruby on Rails, it has built-in migrations, but everybody else is using these tools. Flyway and Liquibase, because they allow you to achieve zero downtime migrations. And in case you don't know what is a migration, migration is the technical term for the amount of SQL statements and code statements that you need to apply into your database to change your database schema from one version to the other. And for us to be able to achieve zero downtime migrations, we need to create migrations that are back and forward compatible, which means that my database schema between versions must be compatible with the next version, and the next version must be compatible with the previous one. And is that possible? Definitely, because many teams are using these things into production. And to achieve that, you need to break your huge SQL script that you use to like email to your DBA or attach to a Jira issue. You're not allowed to do that anymore. Now you have to break that in the smallest possible batch size, which means that for most of the cases, each one of your migrations will have one single SQL statement. You also have to avoid locks, because every time you have to update like your table, it has a billion rows and it takes 5 minutes to update that. 5 minutes of update means 5 minutes of lock time and means 5 minutes of downtime. You're not allowed to do that anymore. And to avoid that, you need to shard your updates, which is a very fancy word in the data world, just to say that if you're used to be updating a billion rows at a time and it takes a long time, now maybe you have to shard these updates into 1 million at a time or like 100,000 at a time. It really depends. You have to rehearse your migrations in a test environment to check how much lock time is allowed in your production database. But I know that some databases, like some versions of Oracle, depending on your statement, it doesn't even lock your database. So depending on the technology that you're using, you might not even need to shard that. But all of the techniques that I'm going to show you, they can be applied to any relational database, and if you change the terminology, can also be applied to any other kind of persistent storage. So, if in the past you used to just rename a column into production, you're not allowed to do that anymore. You have to change this migration into multiple steps. Each one of these steps will have to be in a different version. So I'll explain to you that very quickly. These are the 4 scenarios that I was able to collect between developers worldwide, how they are applying zero downtime migrations into production. And if you want to have that like in more detail, I have all of them described in my book. So I have a whole chapter just about that. So the basic migrations are add a column, rename a column, change the type format of a column, and delete a column. I'll pass through them very quickly. So first scenario, add a column. Each one of these numbers, 1, 2, 3, and 4, is a different version that you're releasing into production. So first version, add a column. Second version, your code computes the read value and writes to the new column. When I say computing, if you can compute the new value from other fields and from information that the user is inputting, it's okay, or else you choose a default value. Third step, you update the data using shards. And fourth step, your code reads and writes from the new column. If you're able to do that, you will be able to achieve zero downtime migrations because between each one of these versions of your software, your database schema is back and forward compatible. So you can have in a blue-green deployment, you can have two versions of your software working at the same time, and the data will be compatible with the old version and with the new version without problems. And just in case you want to know, between each one of those releases, of course, you open your database CLI and issue like multiple select statements just to check if your application is writing the right thing into the right columns. So this is not the only way for you to be achieving zero downtime migrations, but this is also the safest possible way for you to be doing that, because this way you never lose any kind of data into production. The previous version of your data is always there. In fact, it's so safe that some teams started to use this kind of migrations not only to modify the columns or the structure of the tables, but also, well, I need to implement a new algorithm into production, and maybe I have to like calculate something and save to a column. I don't know if the new procedure is going to calculate the value correctly. So what they do, they create a new column and they make both algorithms run in parallel into production, so they can access, well, the previous version is still reading from this column that the new one is writing to here, so they compare if the values are equal or are semantically correct. So that's the safest way for you to implement different algorithms into production too, because you never lose your data. And second scenario, rename a column. First version, add a column. Second version, your code reads from the old column and writes to both. Third version, copy the data using small shards. Fourth version, your code reads from the new column and writes to both. Fifth version, your code reads and writes from the new column. And sixth version, delete the column later. You don't immediately delete the column after you perform your migrations. You simply mark the column for deletion, and maybe on the next maintenance window, if like in the past 2 months nobody's really using the value of the column, you can ask a DBA to go and delete that after performing a backup, okay? Because deleting a column is a destructive statement. You don't want to do that in your production database, okay? So this is the way for you to rename a column. I know many of you might be wondering, does it really work? And to be very honest, to all of the people that I've talked about, to all of the people that have read my book, so far I have received some tweets and email questioning. I don't think it worked, but I'll try. And for everybody that tried to implement these migrations, it worked successfully for them too. So I strongly suggest you to try. To be very honest, most of the teams that I've talked to create this collection, I didn't create this, I just collected the things that people were using to production. Most of the teams that were using this kind of migrations were startups. But I'm very happy to say that in the past year at least, I've seen reports of enterprise software developers using that also to maintain their legacy databases with monolithic systems. Okay, so this is the second scenario. Third scenario, change type and format of a column, and you can see a pattern here. That's exactly same steps for the migration. It's a good thing because you're always rehearsing the exactly same steps. And the fourth scenario is delete a column. You don't delete a column in production. You never do that. You just stop using the read value, but you keep writing to the column just in case your previous version still needs to be running. Your previous version still needs the value from the column. And if everything went well, maybe in a later version you can stop writing to the column and mark the column for deletion. So in the next maintenance window, your DBA will be able to successfully delete the column into production. So this is the way that you can achieve zero downtime migrations. If you ask what about my referential integrity constraints, the easy answer is, well, you have to drop them and just recreate everything when all of the migrations are done. And the same applies, for example, for not null constraints. You not only allow it to apply not null constraints after all of the migrations are done. And the question that I have to answer also is, why the hell I am talking about zero downtime migrations if that's a microservices talk? In the past, the downtime of your system was equal to the downtime of your monolith. So if you had some migrations, you only had your monolith to deal with that. Now that you have a microservice architecture and each microservice must own its own database, your downtime is like you have to multiply the downtime of all of your individual artifacts running into production. You're not allowed to have downtime in your entire system just because that small notification microservice is upgrading its database and it's taking 5 minutes to upgrade the schema. So you need to improve the overall availability, but by not allowing to have downtime for like this kind of procedure, which is updating your database schema, right? So you need to apply zero downtime in all of the points of your system. Now I'll start to talk about the microservices part, splitting and integration. And Martin Fowler did a very nice job trying to collect some microservice characteristics from these architectures. And today I'll only have time to discuss one of them, which is the decentralized data management principle, which basically means that each microservice must own its own database. I won't be able to discuss today why you should be doing that, but I assure to you that this is a very, very important thing in any microservice architecture. So the question comes to, well, if each microservice must own its own database and I'm starting from a monolith, how do I extract my microservice database? And I don't have an easy answer for that, because I've just came from DevOps, where I gave a deep dive session telling people how to create your bounded context and extract your database from your monolith into a microservice, but that's a very long talk. And even the next book I'm writing is about this subject too. But after you, and I say that it's complicated because it really depends on your business model. So I can't give you any tips without having the context on which your information is applied, because the answer really is it depends, because you have to have a very deep knowledge of your domain model to be able to say, well, maybe this part of the data is one feasible to be for extraction from your microservice. But after you have decided which piece of information to extract, I can help you today on how to extract and later integrate this data, because data never lives alone. If you have like individual pieces of information, it's not that useful. You need to establish correlation between your data to produce any useful results. Okay? So the basic principle is I need one database per microservice, but I still have a legacy monolithic database. And the answer is that for quite a certain amount of time, your monolith and your microservice will need to be reading and writing maybe from the same data set. And definitely, they will be needing to integrate the data that you have splitted after a long time. In fact, for the lifetime of your system, you have to be integrating this data. As I said, splitting not easy, but how to integrate later. And before I dig into all of the possible models, which are 9 different ones, I'll have to explain to you very quickly a bit of consistency models, which again is an oversimplification of the concept, but it's just for you to understand what I'm going to explain next. So I'm just going to pick 2 different consistency models, strong consistency and eventual consistency. And strong consistency in a distributed environment means that if I have like 5 different nodes in a system and a variable I equals to 3 right now, and I want to update I equals to 5, all of the nodes in the system, they must agree on the new value before any client connected to any node can read the new value. So before everybody has 5, nobody can read the 5. Everybody is reading 3. This is the model that we're used to think that we have when using database transactions. But in reality, strong consistency is rarely achieved even using database transactions. But for didactic purposes, we teach people that we have a strong consistency even when we're using local transactions. And with distributed transactions, in very rare situations, you're using strong consistency with distributed transactions because it doesn't really scale that well. And you learn that in the rest of the world, the rest of the distributed world, usually embraces eventual consistency. And which kind of eventual consistency? Well, eventual consistency, I'm going to pick a very specific case of eventual consistency, which is the case that is used in enterprise information systems. In a traditional eventual consistent model, you can write your information in any node of the system, right? But if you allow that, you can have like data conflicts, which means that you might have incorrect values in your system and you need to have like some conflict resolution algorithm, which is a very complicated thing. So what do we do in enterprise information systems? We use strong eventual consistency, which means that if I have 5 nodes, I pick one of them to be the canonical source of information. I say writes are only allowed on these nodes. and all of the others are allowed to have reads. So if I have 5 in all of the nodes and I update I to equals to 7 here, everybody connected to this node will immediately read 7, but all of the other nodes will read 5. So as the information propagates to the other nodes, this node might get updated already. So now I equals to 7 here and here, but the other nodes are reading 5, and I might have updated I to 9 here already. So here I equals to 9, here 9 equals to 7, and the other nodes I might be equal to 5. So all of the nodes, they might have outdated information except for the right one, but the information is never wrong. What the difference that the information might be outdated, they might differ from depending on the latency of the updates, but all of the values are correct. They might be old values, but from the business perspective, they are correct. And if you think that you can't afford this thing, well, I have to tell you that the world that we live in is always eventually consistent. I was discussing with a group of developers yesterday. Oh, but my business requirements, they don't allow me to have eventual consistency. Then I asked, are you using a web application? I said, yes. So you know that by the time your query finished in your database and you process the results and you show the results to the user, the information that the user is seeing on your web page is already outdated, right? The information is already eventually consistent because what you're seeing is a snapshot of information that happened like 1 second ago. It might be outdated already. So I don't buy this thing. We really need this strong consistency because most of the world that we live is already eventual consistency, and you need to embrace that if you want to talk about distributed systems because that's the default way of doing information integration these days. And I also have to explain to you very quickly a difference between CRUD and CQRS. CRUD is that traditional architecture that you used to have, create, read, update, and delete. They all use the same model. So if you have a customer model, you create a customer class. If you have a customer abstraction, you create a customer class and use the same customer class for all the operations, right? Read and write operations. But then, if you want to have a CQRS architecture, which is a very fancy name for command query responsibility segregation, in a CQRS, you've been using this architecture for many years. You just didn't know that you had this name. Maybe for performance reasons, well, customer has a lot of different information, but my requirement is to generate a report, a customer report. And the customer has like social security number, address history, transaction history, phone numbers, everything else. But my report just needs the ID, the name, and the email of the user. I'm not going to query all of this information from the database, populate a lot of POJOs, customer POJOs, just to read these 3 fields. What I'm going to do, I'm going to create a customer DTO, create a custom query on the database, and populate just these 3 fields of the DTO. Because that's just the information that I need to show to the user to the screen. Congratulations. You just created a CQRS model. You're using customer and populate the values for the rights operations, but you're using the customer DTO and probably the customer service in the query interface, which is another model, to generate this customer DTO for you. So you have separate models for reading and writing. If you ever created a database view or a materialized view in your database because it was easier for you to aggregate like your results in your database and just query directly from a view later, congratulations. You created a CQRS model. We just didn't know that it had this name. This is the simplest possible model. You just create using different classes in your code for the CQRS, but you can also have CQRS with separate data stores, which means that now you're writing your data into one set of tables and columns, and you're reading your data from another set of tables or columns. That's what happens, for example, if you create a materialized view. That's a CQRS model with read data stores, and surprise, this is the traditional way for you to split, distribute, and later integrate data in a microservices architecture. This is the most popular and effective way of you to integrate your data in a microservices architecture. And very quickly, because I only have 6 minutes right now, I'll have to explain about CQRS and event sourcing. Event sourcing is the traditional architecture in which the state of your data is not stored anymore in just a single row and column of your database. The state of your data is a stream of events. Classical example is a bank account. You never store the amount of money that you have in a bank account in just a row in your table. Your bank account, the information that you have in your bank account is a transaction log. So you have multiple debit and credits, and if you want to know how much money you have in your bank account, you start from zero, and you just apply the debit and credits all the time to check how much money you have now. So it's a very nice architecture to know if what happened. So you have like a free auditing log, you have a free time machine if you want to know how much money you had to any given moment in the past. It's very fast for writing because that's an append-only table, but you bet it's very slow for reading because every time you have to calculate everything over and over again. That's why usually in systems where you have event sourcing, you always create a CQRS read data store, which is a cached copy of how much money you have in your bank account. So you update here, it may be asynchronously, you update the amount of money that you have in bank account, and the banking system works this way. How many of you have tried to do that? You go to the ATM, you withdraw some money, and immediately you try to check on your mobile phone. Yeah, the money is not there anymore, but in your mobile phone, you still have the money in your bank account because all of this information is updated asynchronously. They use a CQRS read data store, but the true source information, in the end of the day, you bet, the bank knows that you withdraw that money because it's going to, worst case, conciliate all of the results during the nights. And after this quick explanation, I'll have to dig through 9 different scenarios that people are using these days to integrate and create the CQRS read data stores. And before I do that, I'll explain to you in all of the, not all, but like 95% of the teams that I visited that were migrating to microservice architecture, the typical path is that I have a monolith, I extract the customer information, and I create a customer microservice. But since I'm a nice architect, all of the operations for the customer information are done through a DAO. So all I had to do is, well, customer microservice creates a REST endpoint with the customer information. My DAO now is issuing HTTP requests for the REST information. I get it back, I deploy that into production, and I fail because it doesn't perform well. It doesn't scale. Well, we have a problem. What developers do? Well, we have a performance problem. What we do? We add cache, right? So we have more problems now. So now we have an internal cache. People don't realize, well, internal cache is not big enough, but it's performing better. So what do we do as next step? We create an external cache, right? So now the cache is big enough, but then you realize, well, performance is not the problem anymore. But then you realize, well, customer DAO is not the only way the only place where you use the customer information. I have a lot of different SQL reports that I have here. All of them use it to have joins with the customer table. And now I have to change all of them because the other information is in my SQL database and customer now is in my key value store. So I have to join this information now in memory, which is completely clumsy. And then the last step is people realize, why don't I create a CQRS read data store directly in my database so my joins can keep working? That's the path that most of the teams have done because enterprise systems that have like very complex reporting requirements, you need to use a SQL database and it's much easier for you to use that information if it's already on a relational database. So the discussion here is, how do I create this CQRS read data store where it's needed? These are the 9 different strategies that people are using. And I'll have to talk even faster before they cut me off. Because the first alternative is shared tables, which means that monolith and microservices are using the reading and writing from the exact same set of tables. You might want to consider that a hack, because that's a perfect excuse for not changing anything anymore. I can't change the tables because the microservice is using that. The microservice team says, well, I can't change the tables because the monolith team is using that. So it's just a hack, and I strongly suggest you, if you're doing that, you change that as quick as possible. Next strategy is database views. You have your microservice, you have monolith. Maybe you want to create a database view in your monolith from your microservice data. And that's the easiest one way to implement. You have the largest support from DBMS vendors. One database must be reachable by the other. If you're using Oracle, it means that you need a DB link. I know many people curse me for that, especially the DBAs. But I've seen people using that in production. And depending on your latency and performance requirements, it works. Okay, next strategy, Materialized Views, which performs better usually than views. And in many enterprise database systems, Materialized Views are implemented as true tables. It just changes the way that you update the things. So they offer better performance. It might be strong or eventually consistent. If you can update on commit, which I don't recommend, which is because it's a performance killer. It can also be updated by a trigger interval. Every 30 seconds, 1 minute, 5 minutes, for half an hour, doesn't matter. You just batch the changes from your source database to your CQRS read data store through the Materialized View. And I've myself did this into production, and it worked even in a use case where I had a data center on-premise and one information system running on Amazon. I was able to create a DB link between Amazon and my local database system and update that like every half an hour because we didn't have very strict performance requirements and the data changes were small. It worked like perfectly, and it took only half a day to implement that. So it was a very nice solution at the moment. Nobody heard that. And you also have database triggers, which is a kind of code. Every time you commit here, you just propagate the changes. I usually don't recommend that, but some people use that successfully, which means that for every change that you hear, you change your CQRS read data store in the other side. It only works for point-to-point integration, and it doesn't scale very well, right? Because if you start to have multiple endpoints to update, you have to create custom code into each one of them. And every time you change the read data store, you have to change it here. Every time you change the microservice, you have to change all of the read data stores. So it doesn't scale. If you have only one endpoint for integration, it might be feasible. But again, I don't consider that a good practice because you have a tight coupling between your endpoints. Transactional code can be stored procedure or distributed transactions. I consider this to be a hack, but some people are using that successfully, so don't judge. But again, it only works for point-to-point integration because it doesn't scale. Since it's custom code, you have to be changing all of the endpoints every time any of the endpoints change. But it works for integration, right? Another way is ETL tools. If you ever used ClickView, Pentahole, Dashbuilder to create your aggregation reports like data warehousing for something like this, if you already have a person on your team that is responsible for the ETL tools and you have a lot of ETL integrations and you just need one simple integration for your microservices, maybe it's just easier for you to create just another ETL integration for you to perform and create your CQRS read data store. But if you have multiple teams that need CQRS read data stores, this tool becomes unfeasible because it's very hard to manage. And if anything went wrong, it's very hard for you to manage what's happening with your ETL integration. So it can be used. I've seen teams using that, but it's not a very robust solution. This one is one of my favorite, data virtualization. If you want to have like a read data store here, you just create a virtual database on top of your physical database so that both ends can read from the virtual database. And virtual database can be customized for each microservice. This one is my favorite because I've talked to 3 different teams that already had data virtualization solutions, and they told me that their experience was great because one of the hard things of trying to split data is that if you did it wrong, you're screwed, right? It's very hard for you to keep your system running if you split your data wrong. But if you're using virtual databases, if you split it wrong, it went badly, you just have to delete the virtual database and start it over again because the physical database never changed. So it's a very safe way for you to achieve that. And I've talked to 2 different teams, 2 here in Europe and 1 in the US that successfully applied this integration in production. Well, I'll have to skip that. Event sourcing. Event sourcing, as I said, is a technique where you already model the right operations in your system as the right event. So it's very easy for you to propagate these domain events into your message bus. So each one of your endpoints can just read the event and update the local data store. But be warned, some people are advocating event sourcing as a solution for everything. I have some very bad experience with event sourcing, and I visit many teams that had it too, because people don't realize, well, event sourcing, you're propagating your events through a message bus. Since I'm using a message broker, I have low coupling between my endpoints. People don't realize that if you have a monolith, the coupling between your modules in the system is the code. It's very easy to refactor, right? But if you have messages, the coupling between the endpoints in your system is the type and the semantics of the messages. Every time you change the type or the semantics of the messages, you have to change all of the endpoints in your system, right? If you add a new event, you have to change everybody because everybody needs to be prepared. If you change the type of information, you have to change everybody too. So even if you're using a message broker and using distributed messages, you have a coupling. So I only advise people to use event sourcing if you have a very mature domain model. You know that your domain model has been stuck for the past like 5 years, not going to change. You're not going to add or change events like daily or monthly in the next years. So maybe it's safe for you to be doing that. Or else, I would suggest don't use like domain events, which will give you like semantic power. Use low-level events like insert, update, and delete, because these type of changes, these type of events, they don't change. The worst case scenario is going to, if your domain model is still evolving, you will change the type, but you will change the type of information, but you won't add new types of events in your system. Okay, that's some of the considerations. And last of all, I had a demo, but I'm over time. I won't show. Change that capture is a set of tools that are perfect if you have a legacy system and sometimes you don't even have access to the legacy code, but you need to perform some integration. That's especially the case because some people say that, well, my monolith is so screwed up, I can't change that, but I have new requirements. So maybe the best practice is to create a new structure, which could be a microservice, and to build that in a new technology, different technology, so I don't have to mess with the monolith. But if you need to integrate the data from the monolith, what do? You use a CDC tool. CDC tools are tools that plug directly into the database transaction log, and they start to read from that and propagate low-level events such as insert, update, delete, and alter table, and everything else. So they propagate that through a bus, and all the other endpoints on the system can read this message and then consume and create their own CQRS read data stores. And the demo that I wanted to show is that now we have a very nice open source tool called Debezium. Debezium is called DB, and they wanted Debezium to sound like a chemical element, so they call it Debezium. So that's the origin of the name. So Debezium is an open source project that currently supports MySQL, PostgreSQL, MongoDB, with ongoing support for Oracle and SQL Server. So basically, you just plug to the database transaction log and start propagating all the changes through the bus, so you can easily consume that. And Debezium uses Kafka, so you have like a persistent and ordered message bus. So each of the consumers can consume in the messages in their own pace. So it's a very safe way to be achieving that. And sorry for being very over time, but that's what I want to show you. If you have more questions, I'll be more than happy to answer that, because I'll be here for today. I'll be here tomorrow too. We have another talk. And well, that's it. Thank you very much.